Hello everyone, let us look at the new topic, study flows under the influence of gravity. Before discussing the study vertical infiltration and evaporation, let us recapitulate what we have understood from the previous lectures. We have seen that the flow takes place from higher chemical potential to the lower chemical potential. So the chemical potential, which is described using symbol mu, which has units of joule per kg or joule per mole. So when this chemical potential is described as energy required per unit volume, so this is written as joule per meter cube. So as joule is Newton meter, so which will have units of Newton per meter square or Pascal. So that is the reason why the chemical potential often we represent as the matrix suction or osmotic suction we represent with pressure terms, kilopascals, and this also can be represented as energy per unit mass or weight. So joule per weight when it is written in terms of Newton, so this is this has units of meter. So when we talk about matrix suction head, osmotic suction head, or the total head which has units of meters, so either you could represent in terms of pascals or in terms of meter. The conversion we have already seen, the conversion is simply by multiplying gamma W here. So if you multiply with unit weight of water, that is kilonewton per meter cube, you will get the units for energy per volume. So as we have seen, the total head controls the flow. Total head consists of the elevation head, matrix suction head plus osmotic suction head. So these two are considered as pressure heads in our earlier basic fluid mechanics, plus velocity head we ignore in our soil mechanics because the velocity gradients are negligible. So when there is no chemicals present in the pore solution, the osmotic head component is 0, and if we conduct a horizontal flow, then the elevation head component is 0. So total head consists of only matrix suction head in that particular case. So this we have seen. For flows, we have utilized Darcy's law, Q equals to minus K I. The K we started writing in a functional form as K of Hm, and I gradient is the total head gradient dHT by dx if it is horizontal flow. If it is a vertical flow, you can write corresponding independent variables like Z. So this is a modified form of Darcy's law for unsaturated flows, and we have seen that the head distribution with respect to space is highly nonlinear, even if we consider a linear form of hydraulic conductivity function. So then let us now look at what happens to study vertical infiltration and evaporation. So as earlier said, in the field it is possible to have steady flows depending on the boundary conditions of the system. So if the water table is located somewhere here, and this is the ground surface. So here at the water table, the Hm, there is a matrix suction head component is 0. So if this is the reference state, the Z, that is the elevation, is considered from here onwards. Z is also 0, and we can consider the sign convention as positive upward. So whenever there is a evaporation that is taking place, so then we consider the flux is positive, and if the infiltration is taking place, then we can consider flux to be negative. We can choose any sign convention. Here at Z equals to some height, say Z, capital Z, the Hm is equals to very high, Hm, or very large value of matrix suction head. So for the vertical flows, same equation we can consider. the Darcy's modified Darcy's law we can consider. So, for the steady state vertical flows, the Q, the flux is equals to minus K dH T by dz. So, as this is a total head which consists of matrix suction head plus Z if we consider upward positive. So, this is equals to minus K dHm by dz plus 1. Here Q is constant and hydraulic conductivity needs to be expressed in functional form K of Hm or K of theta, and Hm also need to be expressed in functional form. So, therefore, if Q, a steady flux, either steady infiltration or steady evaporation that is taking place, and the soil water characteristic curve, that is Hm of theta and K of Hm or K of theta, that is a hydraulic conductivity function. If all these three things are known, then the variation of matrix suction head with elevation can be obtained. If these three things are known, so then we can obtain the variation of matrix suction head with the elevation. Further, this can be simplified for estimating the variation of dz. Dz equals to, this can be written as this can be simplified as minus Q by K and minus 1. So, I will write it this way, is equal to dHm by dz, or dz equals to dHm minus dHm by 1 plus Q by K. So, when you have a hydrostatic condition, the hydrostatic condition is that the hydrostatic condition happens when Q is equals to 0. Under hydrostatic condition, that is when Q is equals to 0, the dHm by dz, so the variation of matrix suction head with the elevation is equals to minus 1. So, which is similar to, I will discuss this. So, second thing, when the soil is completely saturated, then dHm by dz is 0 because Hm itself is 0. So, therefore, the dHm by dz has bounds from minus 1 to 0. So, what exactly this indicates? For example, when you plot the Z, say in meters, and Hm, the matrix suction head in meters. So, then the dHm by dz equals to minus 1 is, so this follows 1:1 line. So, as a matrix suction head is negative, so therefore, so this is negative meters. So, then this is dHm by dz equals to minus 1, or this is simply 1:1 line it follows. So, this is a hydrostatic condition. So, in the hydrostatic condition the flux is 0. So, therefore, dHm by dz equals to minus 1. So, this is just similar to when we have a capillary tube inserted in a capillary in a beaker of water. So, then the head variation, so this is linear, this is positive and this is negative. So, here this is Z, so this is Hm. So the dHm by dZ is minus 1, this is hydrostatic condition. So similar to this, the hydrostatic condition exists when there is a flux is 0. On the other hand, when the soil is fully saturated, the Hm itself is 0, so it follows this line, this particular line. So this is Hm is equals to 0, our soil is fully saturated. So soil is fully saturated, therefore dHm by dZ is equals to 0. Then we can derive conditions for the limits for K, hydraulic conductivity. What should be the values of hydraulic conductivity, or what values of hydraulic conductivity we can consider for the determination of this elevation. So for the dHm by dZ equals to minus 1, this can be written in this form. So K equals to, from this particular equation, K equals to minus Q by 1 plus dHm by dZ. So here when the hydrostatic condition occurs, or when Q is equals to 0, the flow does not take place and dHm by dZ equals to minus 1. So when fully saturated condition exists, then Q becomes Ks. Minus Ks, it depends on whether you are considering infiltration or evaporation. This negative sign is for infiltration or evaporation. So the maximum value of K is equals to Ks. So K varies in this manner. K should be less than or equal to Ks and greater than Q. So in that range the K can be considered. So further the equation can be solved for estimating the variation of matrix suction head or total head with respect to elevation by integrating this particular equation. dZ equals to minus dHm by 1 plus Q by K. So this particular equation can be integrated if we have the functional form, well established functional forms for Hm of theta and K of theta. So this negative sign, if I take it out, so this is varying from say 0 to some depth Z, and this is varying from 0 to Hm. And this integration can be solved if we have the functional forms for K and Hm, Hm of theta and K of theta or K of Hm are known, then this can be solved. If the SWCC discrete data are available, then this can be solved by writing the summation. This can be written as minus sigma I equals to 1 to n delta Hm of theta I divided by 1 plus Q by K of theta I. So let us solve one problem to understand how the matrix suction head varies with elevation. So let us assume the following data. The variation of theta with matrix suction head in meters is known, and the hydraulic conductivity data is also known. When the Hm is close to 0.001, that is near the phreatic line. So this is the ground surface and this is Z equals to 0. So at this point the Hm is equals to 0. So this is a very small value, Hm equals to 0.001 meter, and the corresponding theta is 0.41. So that means this is equals to the theta as saturated volumetric water content. So then K is equals to Ks, that is 5 into 10 power minus 7 meter per second, and similarly other data, when the head increases, the matrix suction head or matrix potential increases, so the theta value decreases 0.38. When the matrix suction head increases, the theta value decrease, so 0.35 for minus 1.5, and this is 0.32, this is minus 2.5, 0.29 minus 4, 0.26 minus 6, this is 0.23 minus 10, 0.2 for minus 20, 0.17 for minus 60, 0.15 for minus 120. The corresponding hydraulic conductivity data is also available, which is 5 into 10 power minus 7, 3 into 10 power minus 7, 2 into 10 power minus 7, 9 into 10 power minus 8, 5 into 10 power minus 8, 2 into 10 power minus 8, 3 into 10 power minus 9, 3 into 10 power minus 10, and 1 into 10 power minus 11. So, this data is the drying data, which represent hypothetical data for well structured clay loam. The data is taken from Marshall textbook 1996. From this reference the data is taken, and slight modification in the data might be there. This is hypothetical data. So, from this we can estimate, because we have a continuous distribution of variation in matrix suction head with volumetric water content or vice versa, and the corresponding hydraulic conductivity is also known. This test data can be obtained by conducting pressure plate tests on a given soil. Initially, when the soil is taken at fully saturated state, and when the UA, the air pressure is gradually increased, then the outflow data can be utilized to estimate the hydraulic conductivity by estimating the slope of the variation in the UA minus UW from initial state to the final state, and the amount of water that has come out from the system. From that we come to know what is a volumetric water content. From the slope and estimating the diffusivity, we can obtain the hydraulic conductivity. Similarly, SWCC data are also estimated simultaneously. So, this way we can obtain the entire data for drying test. So, as this is the drying data, we can utilize this for understanding the evaporation rates. Assume that there is a flux of, there is a constant flux that exists from the soil. So, there is Q equals to 10 power minus 8 meter per second. So, this is evaporation. As we are considering upward positive, evaporation is positive, and this Q can be substituted directly. Now, this can be solved for the first data. So, this is at depth is equals to 0 itself, and for the second data we can obtain the values minus 0.001 meter, minus of minus 0.5. So, there is a difference between these two divided by 1 plus Q should be substituted positive because this is evaporation. So, 10 power minus 8 divided by K is 5 into 10 power minus 7. So, when we solve this, we get 0.489. So, that is 0.489. So, this is at one point, that is at this point, but we require to sum it up. So, when we sum sum up these two, we get 0.489. Similarly, for the other set of data, second test of data, this is minus 0.5 minus of minus 1.5 divided by 1 plus 10 power minus 8 divided by 3 into 10 power minus 7. So, this is 0.9677. Summing up of all these three gives 1.457. So, this gives 1.457 because here summation is there. So, we are calculating at discrete points at 0.1, 0.2, 0.3, and at any given point what is the total elevation, we are getting this value. So, further, so this can be estimated to be 2.41, 3.76, 5.43, 8.09, 10.4, 11.57 and 11.63. So, this is the data, complete data. So, here in the previous case, when we know the values of matrix suction head at any given point x, explicitly we could estimate what is the HM value. However, in this case we solve it implicitly. We estimate the elevation at which we want to estimate how much matrix suction head is existing. So, this is how we estimate the Z from known values of HM, theta and K. So, then Z and HM can be plotted together to understand the variation of HM with respect to Z. So, this is evaporation data. Similarly, we can utilize infiltration data. Here with the same infiltration flux, the water is entering into the soil. So, this is 10 power minus 8 meter per second. However, as we consider a downward negative, so this is minus. So, this is infiltration is minus 10 power minus 8 meter per second. So, if we have data so, this is wetting data. So, this is how the soil water characteristic of data varied. The hydraulic conductivity data are also available, so which are given here. This continuously decreases as the suction head increases. So, this wetting data also can be obtained from pressure plate operators, where initially the sample should be at dry state. Then as the UA value decreases, at equilibrium when you apply very high UA value, the soil will be at dry state, and as you decrease the UA value, the water starts entering into the soil from the higher entry porous disc, which saturates the soil sample under controlled suction. So, this way we can get the wetting data, and the amount of water that is flowing into the soil From that we can estimate the hydraulic conductivity. So, here also the elevation Z at 0, this is the matrix suction is close to 0, and this is theta s or porosity, and this is saturated hydraulic conductivity. So, other values can be estimated. So, for this is minus 0.001 and minus of minus 0.5 divided by 1 plus Q should be here negative. So, 10 power minus 8 by 4 into 10 power minus 7. Then when we solve, this value is equals to 0.5118, and for this is 0.5263 and this is 0.544 and this one is 0.6 and this one is 1.5, this is 22. So, when you use a summation, when you get the summation, so the capital Z, this is 0, this is 0.5118, same as this, and this is 1.038. So, the summation of this one and this one, and this is 1.58 and this is 2.182, this is 3.682, this is 25.682. So, beyond that it is not required, because the Q value is 10 power minus 8 meter per second. So, here the K value becomes 10 power minus 9. So, beyond this value of Q, the values are not important, and if you consider, you get nan numbers. So, we stop it here. So, then if we can plot HM versus Z for the infiltration test. So, the evaporation data is going somewhat like this, and the infiltration data follows like this. So, the hydrostatic line is this. So, this is 1:1 line. So, this is hydrostatic, along which the dHm by dz is -1. So, the evaporation data is constrained in this part, and infiltration data is constrained in this part. So, this is infiltration, and this is evaporation. So, this is completely saturated. So, your infiltration data would be in between completely saturated and hydrostatic condition. So, in between, that is infiltration, and this is evaporation. So, that means if this is the groundwater table, so the phreatic line, and this is the ground surface, and this line shows the elevation, that is Z upward positive. Now, when you have infiltration, so the variation of matrix suction head is, if the matrix suction head can be shown in this manner. So, the matrix suction head variation is somewhat like this, but on the other hand, this may be your hydrostatic condition. This is the evaporation. This is infiltration. These are all for steady state conditions. So, this is how this can be visualized very well in this particular manner. Now, let us understand the transient flows in unsaturated soils. The transient flows are time variant flows. earlier we have considered steady state flows where the flow is time invariant, that means the flux does not vary with time. At any given point or time the flux is constant. But here in the transient flows the flux varies with time. This condition is before the steady state is achieved. So, in the earlier case where I was discussing, you have a groundwater table and you have a ground surface, a steady influx is taking place, that is steady infiltration is taking place into the ground. So, then initially the water content variation varies in this manner. This is initial water content, and this increases with time, and then at steady state it may establish somewhat like this. So, this is at steady state. So, with time this is T1, this is T2 and this is T3, like that. With time this varies and it may achieve steady state after certain time. So, before it achieves steady state, the variation of moisture, the variation of flux, the flux also varies with time, and that is the transient conditions. Most frequently we found transient conditions in the field because the boundary conditions would vary with time, and also in case of fine grained soils it takes enormous time to achieve steady state even though the boundary conditions remain constant. So, you have a constant flux here maintained and you have a groundwater table here. So, but then it takes enormous time for the flow to take place and a significant time to establish steady state. Similarly, when the evaporation is taking place and the evaporation fluxes are same due to atmospheric conditions, and you have a groundwater table is here, but then it takes enormous time to achieve the steady state within the soil system if soil is fine grained soils. In coarse grained soils it quickly achieves the steady state. So, therefore, transient flows are very important in unsaturated soils. Let us understand how to find out the variation of flux or how to find the water movement in soil in a transient condition. So, the first attempt that was made was by Green and Amt to understand transient flows in 1911. So, Green and Amt they have assumed that, for example, when a laboratory test is conducted where this is the soil column, horizontal soil column. Let us first consider the horizontal flows. When you consider a horizontal column which is connected to a water reservoir, so where elevation of H naught is maintained, the water level of the water head of H naught is maintained, then water percolates into the soil and which travels with a speed of x by t. So, x is the distance at any given point. So, here the x is wetting front distance from the water reservoir. So, this is x equal to 0 and this is x equal to infinity. So, infinite column when it is taken, and when the wetting front moves, so the wetting front location is x and the wetting front moves at a speed of x by t, and the assumption is that the wetting front is a very sharp boundary. There exists a sharp wetting boundary, this is sharp. So, another assumption they made is beyond the sharp wetting front soil is completely dry, and before this wetting front the soil is completely wet. So, therefore, the hydraulic conductivity of this soil can be assumed to be Ks, and the volumetric water content of the soil can be considered as theta s, that is porosity, and here whatever the initial state you have theta I and k is anyway 0. So, that can be considered. So, this is the assumption they make, and Green and Amt they derived analytical solutions for horizontal flow and vertical flows for these conditions. They have utilized the Darcy's law, that is q equals to minus k dH by dx. Here Hydraulic conductivity can be considered as Ks because we are considering the soil is completely wet before the sharp wetting boundary. So, therefore, this is minus Ks dH by dx. So, here the flux, that is volumetric flow rate by unit cross sectional area, can be written as the velocity, that is dx by dt, the variation of this is a movement of moisture within the soil. So, the velocity at which the wetting front is moving within the soil, and this is moves through pores. So, the porosity term should be added, that is theta s, but minus theta I, because initially if some moisture content is there in the soil, then that is theta I, that is equals to minus Ks, and this is initially some I would be there, Hi. So, that is a initial suction head, and this is here the head is positive, that is H naught. So, this is negative head, this is positive head, that is this H naught only, H naught divided by dx. So, that is x. So, therefore, now we can rearrange these terms, x dx is equals to minus Ks Hi by Hi minus H naught divided by theta s minus theta I integration of dt. So, here x varies from 0 to say x, and during the time 0 to t. So, then this is x square by 2, which is equals to minus, or this can be written plus Ks, if this can be written as H naught minus Hi by theta s minus theta I, then this whole thing will be positive and you have time. So, then you can write this one as x equals to 2 Ks into H naught minus Hi by theta s minus theta I whole square root and square root of t. So, this is an analytical expression that is derived for understanding the movement of moisture within the soil in the horizontal column when the test is conducted. So, we can solve one example problem. Here x in meters, t in seconds. So, you can input x as 0.01 meter. This is distance from the water reservoir or where the water reservoir and soil interface exists. So, from that at different locations when the water approaches or when the water appears, that is what we are estimating. For the water movement to 0.01 meters and for the water movement for 0.05 meters, 0.1, 0.5 and 1 meter, how much time it takes can be estimated by substituting into this equation. When the properties of this soil are given, assume that the Ks saturated hydraulic conductivity is 5 into 10 power minus 5 meter per second, and H naught is 0.1 meter, a 0.1 meter head is maintained, and theta s saturated volumetric water content is 0.45, and theta I initial volumetric water content is 0.01, close to 0. So, now when we substitute, x is equals to square root of 2 times Ks is 5 into 10 power minus 5 into 0.1 minus Hi is not given, Hi is say minus 1 meter. So, minus 1 meter head is available. So, this is 0.1 minus of minus, so plus 1 meter divided by theta s is 0.45 minus theta I is 0.01 times, so this is time, and x is given, that is 0.01. So time can be calculated, which is 0.4 seconds. So this whole thing is constant now. When x is varying, the t can be estimated by calculating the x square by 2 ks h naught minus hi by theta s minus theta I. This whole thing is constant. When x is varying, t can be estimated in this manner. So t is 0.4 seconds. When x is equals to 0.05 meters, so then this is 10 seconds, and this is 40 seconds, and this is 1000 seconds, which is approximately 16.7 minutes, and this is 4000 seconds. So this is around 1.1 hour. So this is how we can estimate how the water movement, or at what rate the water migrates in the soil. Similarly, for the vertical flows, we can write in the same manner. Q is equals to minus Ks dH by dx, so dH by dz in this case. So this is similar to the previous one, theta s minus theta I times dz by dt. This is equal to minus Ks. Here the matrix suction head component, that is H I minus H naught by Z, and apart from that the elevation due to gravity, this is and the two, this is infiltration that is taking place. So downward negative we have considered, so minus Z by Z. So here infiltration we have considered, that is why this is minus Z by Z. So this is nothing but minus Ks 1 minus, if you take inside, then this is plus 1 minus, again you can consider plus and you can interchange these terms, H naught minus Hi by Z. So when we rearrange the terms for integration, so this could be Ks by theta s minus theta I integral dt is equals to dz by 1 plus H naught minus Hi by Z integration. So as we know, for integral of 1 by 1 plus a by x dx, or which can be written as integral x by a plus x, either you can add x plus a minus a and then write this one expression as integral dx minus a dx by x plus a, or you can substitute x plus a for y and then dx equal to dy, and then you can write the same expression in the same manner. So that way if we write and then this becomes simply y minus a by y dy. So this is integral dy minus a integral 1 by y dy. So this is integration is y minus a log y. So this is a plus x minus a log a plus x plus c. Similarly, if we write for the same this expression, so this is Ks by theta s minus theta I t is equals to, this is H naught minus Hi plus Z minus H naught minus Hi times log H naught minus Hi plus Z plus C constant. Now using the initial condition, it is t equals to 0, the z is equals to 0, because the wetting front is at z equal to 0 only, it has not started yet. So, therefore, for the vertical case, so this is what we have considered. So, this is the H naught same head which is maintained, and the flow is taking place in this manner. So, the sharp wetting boundary is this, and theta equals to theta initial beyond this, and before this theta is equals to theta s. So, this all expressions are available in Liu and Lycos for horizontal and vertical flows in this textbook. So, for t equals to 0 and z equals to 0, that means this is here only the flow. So, then if we consider that, then C is equals to minus H naught minus Hi plus H naught minus Hi log H naught minus Hi. When we substitute this C into this, we get Ks by theta s minus theta I t is equal to z minus H naught by Hi log H naught minus Hi plus z divided by H naught minus Hi. So, this is for the vertical flow. If we assume any value of z, we can calculate what is the time that is required, or how much time it takes for reaching that particular point. We can solve for the same problem. Instead of x, we consider z in meters, then how much time it takes. So, this is horizontal, and let us say, let me write it again. So, for the z, same depth as a horizontal distance, that is 0.01, 0.05, 0.1, 0.5 and 1 meter. Now, let us calculate what is the time required. If I substitute the values in the previous equation and estimate the time, I get these values. I am reporting it here, 0.397 seconds, which is very close to 0.4 seconds. So, the influence of gravity is not available at this particular depth, and this is 9.7, which is very close to 10 seconds, and this is 37.73, and this is 773. So, which is equals to 12.9 minutes. So, 3.7 minutes saved because of the gravity, and this is 2540, which is close to 0.71 hours. So, the influence of gravity can be seen at higher depths or at higher elevations, at higher depths or at higher distances. So, due to the gravity, the flow is faster. So, this could be easily simulated, and therefore, Green and Amt in 1911 he has provided equations for horizontal flow and vertical flows, and in fact, the Terzaghis capillary raise rate or rate of capillary raise estimation, the derivation is based on this particular expression of Green and Amt. Terzaghi has given later on in 1920s or 30s in theoretical soil mechanics textbook that derivation is influenced by Green and Amt. That is what we can understand from the way the Green and Amt has derived solution for vertical infiltration for transient conditions. So, we will see it in the next class. Thank you.